Welcome to the first part of this journal club series on recurrent neural networks titled The Rise of RNNs. So within this journal club session, we're going to be talking about the general RNN architecture and why we use them. And this part of the journal club session is going to come in two videos. This first video will be more of a lecture style presented by myself, David, and the second video will be a more tutorial style of how to implement RNNs within the Keras framework, and that will be done by Salma. So let's get started.
So as usual, we're going to be looking at our learning outcomes first, and we got a lot of learning outcomes for today. And that's because recurrent neural networks are a big topic in machine learning, and we have a lot of details that we're going to be learning about. So we're going to be revisiting these learning outcomes as we go. So we have these first 5 here, and also 6, 7, 8. But again, don't worry, we're gonna take these one at a time, and we'll see that getting these learning outcomes accomplished won't be so bad. So the problem that's going to motivate our learning about recurrent neural networks is the idea of interpreting the human language. So we can imagine maybe a problem where we have an input data where a radiologist has written some free-form text, so they can just write a sentence about whatever they want when they were looking at some medical images of prostate cancer. So maybe an example would be the cancer is in the prostate and has not spread to the bone. So they're describing how the cancer looks in the image. And what we could do is we want to maybe classify these sentences to see how advanced the cancer is. So we could give it a class or label of 0, which would mean that the cancer is within the prostate only, so it hasn't spread. Whereas the label of 1 means that it's spread outside of the prostate. So, and again, if we look at our example, the cancer is in the prostate and it's not spread to the bone. So can somebody tell me what that class would be? Yeah, fantastic. So that would be, yes, it's class 0 within the prostate. And, so we can also have a different sentence like the cancer is in the prostate and has spread to the bone. And this would have, the opposite classification. So it would have a classification of 1, with the cancer having spread outside the prostate. So this example is, something that can be very common in a biomedical setting. But this type of task is also very common in a lot of other applications, especially, with the voice assistant in your phone. It's very similar. Instead of reading a sentence, it gets some audio, but from that, it needs to not only extract, what the words were, but also possibly what those words mean, and, maybe one of a few tasks that it should do based upon those words. So we could try to solve this problem using a traditional neural network. So we would have, multiple inputs at the bottom of our network where we would want to input each sentence that we have, and then we could have 2 hidden layers fully connected, and then a single output for our classification. So we could see here, we could take that sentence that we saw before, the cancer is in the prostate and has not spread to the bone. Each word gets put into a single input, and then, that output is produced. So we could see that within the prostate is given, and maybe the network could be trained, such that it picks up that has not spread, means that, it's stuck within the prostate. Now, if we send in our second sentence, we could see that maybe the network could pick up on the has spread, and that could help it to know that the output is outside of the prostate. But we can start to recognize some problems with using a conventional neural network. First, we can see that since our sentence is shorter, we don't know what to really put in for our last input there. So that could be hard to do. We also see, maybe some of the challenges of training this network. So if we go back to the original example, we could see that, that input highlighted in purple there kind of was interpreting the word not in some way, maybe those weights and biases help interpret it. But then going back to our second example, we could see that now that has the word spread in it. So very different meanings are coming into that input. So it could be maybe very hard to train this network. And the last thing that we'd want to look at is that if we have a very long sentence, or maybe if we wanted to look at a whole paragraph, maybe we could imagine that our number of inputs could really start to grow quite large. And we could also notice that, that problem of having, different length sentences can really start to present itself if we have very short sentences where we have a lot of inputs that are missing. So we can see that using conventional neural networks can be very difficult. As we said, they can be very difficult to train, especially if we have very long sentences. We would have too many inputs. And also we have this problem of how do we deal with sentences of different lengths. We could maybe just, insert zeros or blanks, once for those inputs. But this could actually make the training of our network very difficult for it to be able to recognize if there's no words to handle the input one way, and if there's just blanks to handle it a different way. So, what can we do? So one thing that we can try to do is kind of like a sliding window technique where we would have a neural network where it can just take a single input. So instead of the entire sentence, it's just going to look at one word at a time. And then what it could do is it could give a classification for each word. And then in order to classify a sentence, maybe we would look at the classification for each word and kind of use a voting scheme. So whatever classification was given the most, that would be the classification for the sentence. So in practice, this would look something like this. So again, we have our two layers, hidden layers in our network, fully connected and a single input. So then we could take our sentence and we'd first feed in the word the, and we'd get a classification. And cancer is within the prostate and the bone. So simple enough to feed it through the network. And we don't have any of these problems of very large inputs or, inputs that are missing. We could just feed it in for each of the words. The problem with this is that to the network, the sentence basically looks like this. And as we could see, if we just got these words thrown at us, it'd be very hard for us to interpret. What's the sentence? What does it mean? We have no idea. And that's because at each point, the network doesn't really remember what came before or what came after. So how do we kind of fix this or make sense of it? So we should look to how we read sentences to kind of understand how maybe the network can start to understand the sentences. So this is by using the idea of what's known as context. So again, if we take this sentence here, the cancer is within the prostate and the bone, we could see that, words, depending on their placement, provide the context. So, cancer is kind of joined within. So that means that, that subject cancer is going to be inside of something. So it's going to be related to something else in the sentence. And, it's related to the prostate. And the fact that we have the word and bone kind of joins up that, the bone, whatever is happening to the prostate is also happening to the bone. So the cancer is in the prostate and the bone. So we can start to see how, this happens automatically when we interpret a sentence. But for our neural networks, we need to kind of provide this implicitly. So maybe we could design a network that instead of just looking at one word, it looks at 3 consecutive words at a time, and that could provide more context. So in practice, what this would look like, again, we could have 2 hidden layers, 3 inputs, and all the layers are fully connected. And we can see we're taking 3 words from the sentence. So, in the case where we have the cancers within the prostate and the bone, maybe this would help us produce a classification for these 3 words. And then we could use a similar voting scheme. But we could see here that, even beyond these 3 words, if we have a word very early in the sentence that relates to the end of the sentence, we can see that, the wrong classification would be given. And it would be very hard to properly classify each piece of the sentence. So what we really want is, the context of that word not to really be brought into the input of this network. But we can see that if we're always looking at 3 consecutive words, that wouldn't necessarily happen. So what we'd ideally want to do is have the entire sentence as context. We'd have all the words kind of joined together, and that would give us what we need. But this kind of brings us right back to square one, where we had that neural network where we kind of input the entire sentence into it. And again, we ran into those problems of how do we work with very long inputs, and how do we deal with variable length inputs, so different lengths of sentences. And these two problems are really the motivation for how we want to work with recurrent neural networks. So we'll just jump back quickly to our learning outcomes roadmap. And as a matter of fact, by going through all these failed attempts to try to classify these sentences, we really hit our first 3 learning outcomes as well. So we've learned the 2 reasons why RNNs are preferred to conventional neural networks, because of that variable length input and the potential large number of inputs. And through this kind of example of trying to classify this sentence, we've been able to learn how to kind of extract some aspects of a given study that suggests that recurrent neural networks should be used as opposed to conventional neural networks. And we've kind of recognized the aspect of what we'll learn to be called the time series data that suggests that using context is really the correct way in order to classify a given data point. So these last 2 learning outcomes, we've kind of only seen one example of them so far in this lecture, but in our lecture later on this week, we're going to be talking about another biomedical example that will give us some more understanding of these second and third learning outcomes. So now we're going to try to solve those 2 problems of the variable length input and having a very long input potentially by going back to our neural network that had a single input. And we're going to kind of modify this network as we kind of work through an example to see if we can try to create a solution. So again, we'll start by inputting one word at a time, and we'll kind of flow that sentence through. So let's imagine that the word "the" is inputted. So we'll show the values going through the network kind of with some different colors. So here we can see first the word "the" is kind of in our input, then it goes through our first layer and our second layer. Now at this point, we don't want to provide an output yet. We've realized that doing that isn't going to really work well for our classification problem. So what we'll do instead is a clever technique where we take those output values from the neuron and kind of copy them off to the side, and we'll represent those with these diamonds. So as we've learned before, squares are input values and those circles are neurons. And where that neuron, consists of the inputs, the weights, the bias, the activation function, and all that. So there's some computation going on within those circles. Whereas these diamonds are just going to represent copied values. So basically the output of those orange circles, the orange neurons, whatever values there is basically just going to be copied and pasted into these diamonds. So now that we have those values in the diamonds, they're kind of just saved there, and we're ready to move on. So now we could take the next word in our sentence, cancer. And that's going to be, again, taken in as input. And we're going to represent that going through the network with the color pink. Now, the change that we can do now is because we have those orange diamonds kind of saved, and that was kind of encapsulating the word "the" as it went through the network. What we can do is we can kind of take those values and we're going to copy them down kind of back to the beginning of our network, and we're going to use them as inputs into our first hidden layer. And these inputs are going to come in at the same time that the word cancer is taking in as input. So both are going to be feeding into the network. And what these diamonds are basically going to capture for the network is allow it to have some idea of what came before the current word as well as the current word going into the network. So this first hidden layer of neurons would have its output values computed using all the values given to it. So those 5 orange diamonds and the pink square. And then these values can travel through the network. And then again, we aren't at the end of our sentence yet, so we aren't going to output. So we'll do the same process again, where we copy our values over to those diamonds, and then they're there and kind of safe for us. And then we move on to the next word. And again, here we would want to use the word is as the new input shown in blue. But again, the context of that word using the cancer is also going to be kind of fed in as input again. And this kind of cycle is what's known as a recurrent connection. So the output of the hidden layer is kind of being fed forward into the next inputs values. So again, we can take just the values of those pink diamonds and the blue square, and they're used to get our next our hidden layers values outputs. And then we can basically just keep running this process through until we get to the end of the sentence. So we can imagine, our diamonds now have some purple values in it, and those values contain all the context of the sentence. And we have our last word getting given to us as input shown in green. So our first hidden layer values could be calculated using all those inputs. So this basically has all the information from the sentence within it. And then we can take those values, compute our next layer, and then because we are at basically the end of our sentence, instead of copying these green values over to the diamonds, we can use them to calculate the output value shown there, and that can give us one classification for our entire sentence. So if we kind of strip everything away, we can kind of see the general structure of this new type of neural network that has successfully been able to process an entire sentence of a variable length. And we could also imagine that if we had a very long sentence, we could just keep repeating this process, and the entire context of the sentence would be read in. And we see that this basically consists of a traditional neural network with some kind of that copying or kind of that recurrent connection kind of going from the output of one layer and then back in at that lower hidden value layer. So now what we want to do is to take this diagram and to simplify it a bit more so that we can kind of package it up as a single concept. So we'll start by working with these layers of neurons. So we can see that we can take all the neurons on a given layer and kind of condense it down into a single block shown there. And then similarly, we can do this for our second hidden layer. And then we can also do it for these kind of copyings that we do. And we'll just show those with kind of the slashed filled in blocks. And then what we can do is we can take those copy values and just represent them as a single arrow. And this is what we would call our recurrent connection within our neural network. And we can simplify this even more by taking all of our hidden layers and kind of condensing them into a single block as shown. So this is what's known as a recurrent neural network, or an RNN. And that's because of that, we have that recurrent connection that's kind of looping back from those hidden layers and kind of being taken in as input, as well as being produced by those hidden layers. This was what would be known as a standard recurrent neural network, and that's where we're going to kind of start our learning together. And we'll see some variants of this kind of structure in our future networks. Also, this representation that we see here of the neural network is known as the unfolded representation of a recurrent neural network, which is one of two types of representations that we'll see. So just quickly going back to our learning outcomes, so where we can see where we are in accomplishing them. Again, we've hit off learning outcomes 1 to 3 already, and just now we've kind of learned through the process of developing a recurrent neural network, kind of how to show it within what it's called as its folded representation. But we can see in learning outcome number 5, we want to learn what this unfolded representation is. So to kind of learn how to represent this unfolded representation of a neural network, we'll go back to our example where we had the sentence, the cancers within the prostate and the bone. And what the unfolded representation is going to give us is a way to kind of visualize our network where we can see all the inputs coming into the diagram at once. Whereas with the folded representation, we can only see one input at a time, shown with the word the in this current diagram. So the first step of making the unfolded representation is first, we take our first word and we put as input. And if it's not the end of the sentence, we take that output neuron off. So we can see that that little circle at the top is now gone. Then what we do is we take our second word and we kind of just copy and paste that folded representation of the recurrent neural network. And we just show that second word being inputted, cancer is shown. And again, here we'll show the purple words kind of representing, the context that the current word in yellow currently has. And again, we have, this isn't the last word in our sentence, so we remove the output part of the diagram. Now what we do is we remove both of the recurrent connections that were between each of those recurrent neural network diagrams and kind of show how it travels forward in time. So or forward to the next word as input. So we can see that the hidden layers for the word those values are kind of outputted, and then they kind of move forward to be given as input for when we're looking at the word cancer. And how we'll start to talk about this is with respect to time t. And we'll kind of talk about this kind of running from left to right, just as if you were, had a graph that was plotted against time. And what we'll start to refer to our sentence as is having, multiple times that these words are at. So a sentence really isn't happening in time unless it's being spoken and maybe we're trying to classify it live. But it's kind of an easy way for us to be able to talk about these recurrent neural networks in a very general way. So we'll index each word within our sentence using a single time. So we could see that the word the is at t equals 0. And again, we'll start at 0 to match all the other indexing that we've done in this course so far. And then cancer could be at t equals 1, let's say. So we'll call this entire sentence, because it's basically happening over time, we'll call it a time series. And another way that time series are often shown is as a graph. So we can imagine in a very general sense, we could have a time series that, maybe there's 5 data points that are happening on a graph over time. Then for a single time or a single word within our sentence, we would call this a single time step. So we could have time step t equals 0, time step t equals 1 so far. And within our time series graph, we could represent this as a single point along the time axis. So we can imagine, that current line is at time step t equals 1. And then for each word within our sentence, we'll refer to that in this course as a data point. So at each time step, there's a single data point for each time series. So again, in our graph, that would be a single point at that single time step. So by looking at these in terms of graphs, we can see how these recurrent neural networks could be used in a lot of different applications, not just for sentences. So now that we have that nomenclature out of the way, we could start to build up more of our unfolded representation. So if you just keep repeating what we've done, we could see, this is up to time step t equals 3. We can see that those inputs and hidden value layers just get repeated, and then we keep having these recurrent connections that go in between each time step. And if we continue this all the way out to the end, we could see that we could have each input at each time step from our sentence be represented. And when we reach the end of our sentence, so we're at the word bone, then what we do is we add on our output neuron, which will be our classification. And then we can see that our entire sentence is represented. And that can help give us, our classification of 1, meaning, the cancer has spread out of the prostate. And we can see that this single classification is given by having the entire sentence being kind of given to the recurrent neural network. And we can really see by these recurrent connections of these arrows kind of connecting each hidden layer to one another, how all of the values within the sentence kind of work together to give us that input. And we can see very clearly here too, if we kind of draw these orange lines on to kind of separate each time step, we can see in total that we had 9 time steps. So we had our final one at t equals 8, but because we started at t equals 0, we have 9 time steps. But if we add do this for a different sentence, where maybe it's the cancer is within the prostate and not the bone, we can see how we can add on another time step, and the recurrent neural network can still produce a single output to be able to provide the classification. So this leads us to be able to kind of cross off learning outcome number 5 from our slide deck, where we're able to draw an RNN in its unfolded representation for a given time series input. But we need to remember that we still have 3 more learning outcomes to go, learning outcomes 6, 7, and 8. So we'll keep on moving on to accomplish those. So one question that we might have at this point is, it seems great that we can use recurrent neural networks to kind of produce these classifications for, a sentence, let's say, or maybe some other tasks that we're doing. But, these look so different from conventional neural networks. How do we possibly train a recurrent neural network? And that's a great question to be asking. Now, what we need to do before we can start talking about how to train a neural network, we need to be able to start figuring out, what part of our current neural network can we actually adjust or optimize such that that training can occur. So we've jumped back to our kind of our detailed representation of the current neural network in its folded representation, so that we can kind of discover where our different parameters live. And we'll do this by looking at the weights of our neurons. So we could adjust the biases of our neurons as well, but we'll just look at the weights in this case. So we can imagine from our input to our first hidden layer, we would have 5 connections, and each one of those would have a weight. So therefore, we'll have a weight matrix. And, using our traditional notation, this will be W subscript 0. Then moving up to our between our first and second hidden layers, we would have, full connections. And these would, again, each have their own weight. And this will be weight matrix W sub 1. Also, going up to our output, we again have a fully connected layer. So we'd again have a weight matrix W2. So here we can already see that we have 3 weight matrices that we could adjust or tune through training. Now we also notice that there is these copyings of those values into the diamonds. So let's take a look at those to see if there's any parameters. So to get those values over into the diamonds, that's a copy operation. So there's nothing that we can really adjust there. It's whatever output comes out of that last hidden layer gets copied into the diamonds. Similarly, going down into to copy our diamonds down to be ready to be inputted, again, back into the network, no parameters there. But we can see when these values of the diamonds get reintroduced as inputs into the first hidden layer, there is a lot of weights that we can actually tune. So this would be, again, a set of weights to basically connect the two layers to one another. And this would be represented with, weight matrix, maybe W sub R for, recurrent. So we can see that we have 4 weight matrices here. So if we kind of go back to our more condensed diagram, we can see how all these weight matrices are still represented there. And we can even write this more compactly again, kind of with the folded representation of the recurrent neural network. And sometimes if we write it in this condensed way where we don't display the hidden layers in their entirety, that kind of encapsulates some parameters that maybe wouldn't be represented as explicitly with an arrow as a connection. So here we can see that W1 matrix is kind of encapsulated within that hidden layer block. So if we have kind of this folded representation of the recurrent neural network where we can see the hidden layers, let's just put this into the unfolded representation so that we can kind of try to understand if we kind of unfold that whole network, where our weight matrices are. So again, for our first sentence or first word in a sentence, we would take off our input. And then for the second word in our sentence, we basically, again, just copy that same folded representation. And then we draw our recurrent connection. So I'll just draw this as an arrow, kind of connecting those two hidden layers to one another. And we could see that there's that weight matrix, W sub R, that kind of represents the parameters that are being used to make that connection. And those could potentially be tunable. And we can see that recurrent connection where the WR is going across a time step. And this would occur for however many time steps we see, where we basically just copy that same representation over and over again until we get to our last time step, and then we have our output. And what this allows us to see is that a lot of our parameters are actually repeated. So we can see W sub 0 is repeated for each input. W sub 1 is repeated between each of our hidden layers within each time step. WR is repeated across every time step for that recurrent connection. And then we have W2 represented only once when it goes up towards that output. So this allows us to quickly cross off another one of our learning outcomes, and this is basically to be able to identify the connections that have different or identical weights on an unfolded recurrent neural network representation, which we saw with all those weight matrices. So now we can move on to try to see, now that we know where our parameters are, how we can try to adjust or optimize them. So now that we have found where all the parameters that we basically need to optimize during training are, now we can start to think about, okay, how are we actually going to, in principle, train this network? So like all other neural networks, we train using a training sample. So here, the training sample would consist of, an input, maybe a sentence, cancer only in prostate, and a known output. So in this case, it would be that classification 0. It's within the prostate. So then what we would do is we would take our input, cancer only in prostate, and we'd have it feed forward through the network with whatever values of W0, W1, WR, W2 that we have. And let's just say that value comes out to 0.61 out of our final neuron. And then what we do is we would compare this to our known output that we wanted to get for our we wanted our network output. And these would basically give us our little y values, so the output, and our big y values. So that would be like the target output that we would want for our network. So then if we want to start trying to adjust the weights of our network, we need to start applying the values of our hidden layers and our inputs, as these are the values that we're going to be kind of working with the gradient descent and back propagation. So just like all our other networks that we worked with, the input's going to be X, and the hidden layers are going to be H0, H1. So those are the values of the outputs of the neurons of those hidden layers. So we put them in for time step 3 there. But then in time step 2, if we put in the input, what we can notice is that both of these are called X. And this is going to be really confusing for us to have two variables that have the same name. So what we're going to do is we're going to add a subscript to them that's going to correspond to the time index. So you know that 1 at time step equals 3, that's going to be X subscript 3. And similarly, time step 2, X subscript 2. And we can do this for all of our inputs. So X0, X1, X2, X3. Simple enough. Then we can also add in these hidden layer values, H0 at each time step. And we could see that, for these different hidden layer values, they have the same parameters, W0, WR, but the input coming into them is different. So they have different input values, so X2, X1, X0 from the actual sample that we're working with, but they also have that recurrent connection that will always have different values coming in from the previous time step. So these will actually be different values from one another, but we can see that their variable name, like the X's, is all the same. So again, we will introduce a second subscript. So the first subscript will kind of still stay locked with which layer is it, so layer 0 or layer 1. But the second one will correspond to the time index, just like the X's. So, for the one for the H value shown here, it has H0 for layer 0, comma 3, because it's in time step 3. So we can apply this for all of our layer 0 hidden values. And then what we would do is apply the same technique for the layer 1, so the second hidden layer. And again, we would have H1, but all these values have the same variable name, but they would actually take on different values at each time step. So we add in that second time index to help differentiate them. So now we have all of the individual values that are basically present within our recurrent neural network for the given sample that we have. And we could easily imagine that we could, if we had a sentence with 5 words or 6 words, we could easily expand this recurrent neural network, as we've learned before with the unfolded representation. So now to start adjusting our parameters, what we want to do is, of course, first look at the loss. So again, loss is designated by the variable L, and we've learned, that we could have different loss functions, but here we'll just do the sum of squared errors like we've done before. So again, we would just take our, our actual output value and our target, and we would just subtract the difference between them and take the square. Then we would want to look at the parameter that we're specifically interested in changing. So when we actually train a recurrent neural network, we would want to, of course, optimize all the parameters, but for this example, we'll just look at a single parameter. So we'll look at parameter W sub 0, and specifically with the superscript 0, 0. So what this basically means is that it's the weight of a single neuron, shown in a little diagram of that first hidden layer there. So we're going for a single scalar value that we're trying to tweak to make our loss better. And remember that we use gradient descent. So this is basically the idea that we want to take our our parameter value W sub 0 with the 0, 0 in the superscript. And we basically want to change its value to be updated by the gradient, which is that upside down triangle multiplied by LR, the learning rate. So this is basically the update step that we take to basically try to optimize our loss. And remember that that gradient term is specified by taking the derivative of the loss with respect to that specific parameter that we're interested in updating. So in this case, W subscript 0 with the superscript 0, 0, so a single value. But remember that if we were doing this in practice, that specific parameter would be replaced with all of the parameters. So we're trying to optimize all of them. So that gradient would be more complicated than what we'll show here. But moving forward, where we're trying to understand how to train these networks, we aren't expecting you to all know the math in depth and be able to train a network. It'll be more about the final conclusions that we reach about training a recurrent neural network that we'll talk about when we revisit the learning outcomes. So now we are going to calculate the gradient. So if you see at the top left of the slide, we're going to start to be basically writing out a large equation to kind of specify how to calculate this gradient. And this is going to become quite a large equation. So again, don't be too scared of the mathematics. We're going to show it in the diagram as well. And again, we don't want you to be able to replicate these mathematics, but they're really here to just be able to show how a recurrent neural network would be trained and some of the theory of it and some of the outcomes of that theory, which are really important and we'll talk about. So again, the gradient is the derivative of the loss L with respect to the parameter we're interested in optimizing. So if we look, we see that the loss is in terms of the output of the network, little y. So then, in order to keep computing this gradient, we'd have to basically keep taking the derivative through that function of y. And we know that y has the parameter that we're interested in optimizing, w, within it. So we kind of expand our derivative as shown, where we take the derivative of loss with respect to y, and then we take the derivative of y with respect to the parameter. So we're basically just expanding out this derivative. And we can keep moving through our neural network. So we know that y is given by the values within h subscript 1, 3, so the last hidden layer at the last time step. So then what we do is we take the derivative of y with respect to these hidden layer values, and then we take the derivative of the hidden layer values, h1, 3, with respect to the parameter we're optimizing, the w term. And then we do this for another step down the next hidden layer, and we can see how our derivative keeps expanding with kind of the same pattern that, the denominator of one term becomes the numerator of the next term. And what we can see at this step is that our h subscript 0, 3 terms, so the hidden layer values of the first hidden layer at the last time step, are actually directly computed using h0. So we can see it highlighted in pink there, and we can see that this basically means that we've reached the end of that gradient calculation that we need to perform. We've kind of reached the parameter we were trying to take the derivative of. But we can see that there are actually two values of w0. So we've only kind of reached the end along one of the possible paths that helped compute h sub 0, 3. So what this means is that we actually need to add on another term to our gradient where we kind of try to trace the path to this second w0 term at time step equals 2. So we can see how that derivative kind of got that addition term. So that was basically saying for getting to the w0 term at t equals 3, that's kind of that first piece of the derivative, plus we need to take, another derivative journey through to the W0 term in t equals 2. And that's where that addition is. So we can start to do that same derivative pattern where with the numerators and the denominators to try to reach that term. Now what we want to do is simplify this mathematics a little bit. So we'll take that piece of that gradient that kind of got us to the derivative in the time step t equals 3, and we'll take that as the derivative of the loss with respect to the parameter w0 superscript 0, 0. And then we'll give that whole term a little t equals 3 to say, you know what, that was the derivative. If we're just looking at t equals 3, that got us there. So that helps us kind of package up our gradient a little bit simpler. So with that all done, then we can start to look at, again, tracing the gradient through to time step equals t equals 2. So again, we can keep on expanding this derivative such that we reach the first hidden layer at time step equals 2. And then we see that again, we've kind of reached our goal. We've reached parameter w0 superscript 0, 0. We've gotten to the parameter that we want to optimize. So that's great, fantastic, exactly what we wanted to do. But then we see that we run into the same problem again. So we've reached w0 for time step t equals 2, but there's another w0 term in t equals 1. So we're not done. So what it means that we have to do is we can, take this term that got us to time step t equals 2. We can package it up again very similarly to what we did for time step 3. We take this derivative of the loss with respect to the parameter and we give it t equals 2 to say, just to get us to the second time step. And then what we can imagine, we can start to see a pattern starting to happen. We have the derivative terms for t equals 3, t equals 2. So again, we add them on for t equals 1. And lastly, t equals 0. And we can see highlighted in pink, now we've kind of gone through the whole recurrent neural network all the way back to the first time step. So this gradient kind of becomes a very large and complex term to try to calculate. But we can see it's kind of broken up into the 4 chunks, one for each time step. Now what we want to do is to look at trying to calculate just one of these time step derivative terms. So we'll look at the t equals 0 term in particular, highlighted in purple. So we'll kind of pick up where we left off from the derivative at t equals 2, where we kind of got to that first hidden layer. So we can see that highlighted in purple here, where we kind of got part of the way, but we want to go all the way back to t equals 0 for this single term that we're looking at, the derivative of L with respect to the parameter going all the way back to t equals 0. So we can see we're about halfway there. And, we could keep on adding on the derivative terms, following the same patterns that we've looked at before, keep on changing up those denominators and numerators. And eventually we will reach all the way back to where we need to get to our W0 term. Now what we can start to see is that a pattern starts to appear in this derivative. We can see within each of these purple terms some common patterns with the subscripts. So we can see in the first fraction of each of these highlighted sections, we can see that the second subscript stays the same, where the first subscript changes between a 1 and a 0. And for the second fraction, we can see that the 0 and 1 are kind of flopped in the first subscript, and then the second subscript, it kind of is a single value in the top one, and then minus that value for the bottom value. All right. So with that, we can write a quick little formula to kind of encapsulate that. So that's shown here off to the right, where we can see that we have this big T value that kind of represents some number, for the first time this pattern appears, t equals 3. For the second time, it's t equals 2. And for the next time, it's t equals 1. So we can write this more compactly using this sort of notation. So this notation is very similar to when we kind of use the summation notation, where we would have that sigma value, like in the artificial neuron. But here we use this big capital pi symbol. And what this means is that instead of, multiplying, or instead of adding those terms one after another, we're going to be multiplying the terms together. So this encapsulates the fact that we took all those, pairs of fractions, and they were originally all multiplied by each other. So then we need a way to multiply them all again. So this is really helping us condense our notation. And what this allows us to do is, if we imagine that we had, a sentence with a lot of words in it. So let's say it has n words in it. We would have a lot of repeated steps within this recurrent neural network, where you have those recurrent connections, those hidden layers repeated all the way up to time step t equals n minus 1. Because remember, we're starting our indexing at t equals 0. So, but then if we want to calculate this derivative term, the derivative of loss with respect to the parameter, and we want to go all the way back to t equals 0, we'd have to travel back through all of those steps to kind of trace through this purple derivative term. Now for our representation of this derivative, where we kind of have found this pattern, this is really useful for us. So what this allows us to do is kind of just slap in this n-1 term shown in pink, which basically says, just repeat the same pattern for basically however many words you have. And then, we have a little piece at the beginning and a little piece at the end to kind of start us off and finish us off, depending on the specific parameter that we're trying to do. So we've now found a very general way to kind of easily represent the single loss derivative term. So with this loss derivative term, we can start to maybe make some ideas of approximate values that this gradient could take on. So we're not going to compute, an exact number like 0.742 or something like that, but we're going to try to look at some general trends that this value could take on. So what we're going to do is simplify our lives a little bit, and we're going to take this first term and the second term that kind of that aren't part of like that repeating pattern of derivatives. We're just going to kind of package those up and say that's term A, some value, and it's not too critical what that value is at this moment. So this simplifies our expression. So now we just have A multiplied by kind of that repeating pattern that's multiplied over and over again. Now what we can do is we can reach inside of that multiplied pattern, and we could say that there is some value that will not exceed. So kind of an upper limit called B. Now the mathematics behind this, of course, do exist, but they're a little bit too complicated to go into this in this lecture or this style of course. There's a lot more involved calculus and linear algebra to kind of develop this idea that there's kind of an upper limit to this value. But suffice to say that there is. So what this can then give us is kind of an upper bound for this derivative term that it cannot grow larger than. So we use this less than symbol to represent that. And we can see that we took that inner repeating pattern and just replaced it with B. So now it's just B being multiplied by itself over and over again. So A times B times B times B times B times B for however many words in the sentence we have. So if we're multiplying the same value over and over again, there's a simpler way to write that, which is basically B to the power of some exponent. So in this case, it's B to the power of n minus 1, where again, n is the number of words that we have in our sentence. So here we have a very compact way of kind of saying this is the value of the derivative. The value of the derivative will never be greater than this. And what we can start to notice is that if that n value becomes very large, that will basically be reflective of the recurrent neural network becoming very deep. So, in a case where we have 4 words in the sentence, n would be equal to 4. But let's say we wanted to start looking at a paragraph, n could start to be, 100 or even 1,000 if it had to start trying to process larger and larger pieces of text. Now, this means is that this derivative term, the derivative of L with respect to W for t equals 0, is that it kind of approaches two values as n becomes very large. So if we start to have longer and longer sentences, this derivative term will kind of go towards one of two values. So if b is less than 1, it'll go to 0. So let's say b was 0.5, let's say. And we could use the complex math to calculate what b was. If we times 0.5 times 0.5 times 0.5, and put it to the power of 100 or 1,000, it would go to the derivative value would go to a very small value. Whereas if b is greater than 1, let's say it's 4, and if we do 4 to the power of 100, again, that term is going to be very large, and it'll kind of tend to infinity. So we can see that unless b is very, very close to 1, we're either going to have this derivative go to 0 or go to infinity. Now, what this is labeled as within the machine learning community is if this derivative goes towards 0, as we learned previously when we were learning about activation functions, this is known as the vanishing gradient. So if that derivative goes to 0, our gradient is going to be 0, and that means that the gradient is almost vanishing. And that's not good because then, we can't really update our parameters because our parameters are updated using that gradient term. And if this derivative term goes towards infinity, that's what's known as an exploding gradient. So the gradient is very, very large, which is not great either because that means our parameters are going to take on very large values and they're going to be swinging wildly around and are going to be very hard to optimize. So these are kind of the two problems that we see that start to occur when we try to train a recurrent neural network. And these two terms, not necessarily how we got here or the mathematics behind it, are important for you to know. So just to know that, for recurrent neural networks, if they become very deep, that the gradient can either vanish, it can go towards 0, or it can explode, go towards infinity. And this is just a mathematical fact of how recurrent neural networks work because of how basically deep of a network they become. So I realize, at this point, maybe everyone tracked along with it. Maybe you didn't, and it's okay if you didn't. Remember, knowing all that mathematics is not necessarily just a general idea of kind of how we got to where we got to. But to wrap it all up, we'll kind of do one last little summary of everything that has occurred. So again, starting with our recurrent neural network, we can see we have various weights, and these are parameters that we basically want to tune. And we would have, some input that could have n words. So, x0 to xn minus 1 for those different time steps. And that would give us some output, 0.61. And we'd compare this to our target, capital Y. And in order to train the network and update the weights, we calculate the loss, using sum squared errors, let's say. And we'd want to, in particular, for our example, update a single parameter, this W0 term. In order to do that, we use a gradient descent method. So we update that W0 term by adding the gradient multiplied by our learning rate. And then the calculation of the gradient is where things start to get difficult. So we take the loss and we take the derivative of it with respect to that parameter we're trying to optimize. And that gives us our gradient term. Now, as we saw for a sentence of n words long, we'd kind of have to split up that derivative into a t equals n minus 1, t equals n minus 2, all the way up to t equals 0. So this is kind of tracing that derivative through to each of the time steps that we saw. And then we saw that, through some complex mathematics, you could kind of get an upper bound for this gradient. And depending on the time step we're looking at, that determines on kind of what the power of that exponent is. So if we're looking at a very late time step, that means that upper bound is going to be, b to the power of 1, which, if b is small or big, not that big of a deal. B will just be b. For time step t equals n minus 2, again, very close to the output. we would have b to the power of 2, which again isn't that bad. But we can see for early time steps, t equals 1, t equals 0, b gets put to the power of n minus 2 or n minus 1. So very, very large values. So if b is not equal to 1, it's either going to be very big or very small. So this, in general, how we could write this is that, for terms at, very large time steps, so near the output, the values are not impacted that much by how big n is. It doesn't really matter. But for, values of, for time step values that are very small, so, near the beginning of the sentence, let's say, then if it's a very large sentence, because that exponent becomes so large, these values start to vanish, or as we saw, it could also explode. And what this basically means is that the gradient term ends up being largely impacted by only the values at the very large time step. So that time step n minus 1, n minus 2, which is very near the output of the network. Whereas the gradient is not affected very much by the time steps, t equals 1 or t equals 0. So the very early values. And what this effectively leads to is the RNN forgetting the beginning of the sentence that we want, because when we're training it, it's not really impacted by any of the inputs that are coming at the very early time steps. And so it really focuses on only training based upon the time steps very close to the final output. And what this basically leads to is, again, the RNN just using the end of the sentence to try to make its decision. So it's basically forgetting the beginning of the sentence before it reaches the end. So this last take home is a very important point to remember about RNNs that we've looked at. And moving into the next lecture, we're going to look at some possible solutions that we would have to try to fix this. So this allows us to check off the last two learning outcomes for our lecture today, and these kind of help frame, what you should really take away from this last part of the lecture. Again, to not know all the mathematics, but really the big ideas, so that the vanishing or exploding gradient problem can cause standard RNNs to be very difficult or even impossible to train. So that's the one big takeaway that you need to know. And also that this vanishing / exploding gradient problem causes the standard RNNs to basically forget the data points from the early time step. So basically forgetting the beginning of the sentence, as we saw. So those should really be the two main takeaways that you make sure that you can effectively do in order to make sure that you know what you need to know from this last part of the lecture.